Hi friends, welcome back to our YouTube channel. Today we have to discuss about flowchart for floating point addition or subtraction in computer architecture course, computer organization course, computer organization and architecture course. To perform the addition or subtraction between two floating point numbers, we require 4 steps. First step is check for zeros. Second step is align the mantissas. Third one is add or subtract the mantissas. Fourth one is normalizing the result. By using these 4 steps, we have to perform the addition or subtraction between two floating point numbers. These 4 steps are included in this flowchart for performing the floating point addition and subtraction. So this up to this point, this is the first step, check for zeros. Next, this one represents the second point, align the mantissas. This one represents the third point, that is add or subtract the mantissas. This one represents the fourth step, normalizing the result. Now we have to discuss each and every step in the floating point addition or subtraction. Now we have to start the addition or subtraction between the two floating point numbers. To perform the addition or subtraction between two floating point numbers, we require two registers. First register is BR register. In that one, we have to store the first floating point number. Second register is AC register. We have to store the second floating point number. After performing the addition or subtraction between the two floating point numbers, the result is again stored in the AC register. This is the usage of these two registers. Now we have to check the BR register. Suppose BR register contains a 0 value or not. That means the first floating point number contains either 0 value or not. Suppose BR value contains 0. That means the first floating point number value is 0. Then there is no need of checking the AC register, because whatever the value that is present in the AC register, that becomes the result. Because of that reason, there is no need of checking the AC register when BR value is equal to 0. So here BR value is equal to 0. We have to end the process, because whatever the value that is present in the AC register, that becomes the result of the corresponding operation. Now, next one, suppose BR value is not equal to 0. BR value is not equal to 0. Then we have to check the AC register, whether AC register contains 0 value or not. When BR value is not equal to 0 and AC value contains 0, that means the second floating point number value is 0. Then what we have to do? Okay, so AC tends to BR plus AC. Okay, so here BR value is not equal to 0. Then AC value is 0. So that BR contains not equal to 0 and AC value is 0. So BR plus 0 is nothing but BR. So whatever the content that is present in the BR register, that can be transferred to AC register. So this step we have to follow. So when we have to follow this step, when BR value is not equal to 0 and AC value is 0, then whatever the value that is present in the BR register, that can be transferred to AC register. After that, we have to check what is the operation we have to perform, either addition operation or a subtraction operation. Suppose we want to perform the addition operation, so nothing can be done. That means whatever the value that is present in the BR register, that is transferred to AC register whenever we are performing the addition operation. Suppose we want to perform the subtraction operation. Okay, so then what we have to perform? So here AC tends to, so AC minus BR. Suppose we want to perform the subtraction operation. Okay, so here AC value is 0, BR value is not equal to 0. So AC value 0 means 0 minus BR. So 0 minus BR is nothing but minus BR. So then whatever the value that is present in the BR register, that can be complemented. So that complemented value can be transferred to AC register. So it is similar to, so AC value is 0, BR value is 10. So AC minus BR. AC minus BR is nothing but 0 minus 10. That is nothing but minus 10. Okay. So whatever the value that is present in the BR register, that can be complemented. That complemented value can be transferred to AC register. Okay. So this is nothing but minus BR value. Okay. So for getting the negative sign, we have to complement the sign bit of the accumulator. Okay. Sign bit of the accumulator is AS. Okay. For getting the negative result in the accumulator, we have to complement it. Okay. The complemented sign bit value of the accumulator register can be transferred to AS while performing the subtraction operation when BR value is not equal to 0 and AC value is equal to 0. Okay, then we have to stop the procedure. When BR value is not equal to 0 and AC value is not equal to 0, then we have to do this process. First, we have to check the exponents of two floating point numbers. So this is the first floating point number and this is the second floating point number. In that one, the first floating point number exponent value is 3. That can be denoted by small a. Small a is equal to 3. Second floating point number exponent value is -1. That can be denoted by b value is equal to -1. First floating point number Mantissa is 0.583123. That is denoted by capital A. So capital A is equal to 0.583123. Second floating point number Mantissa is 0.123000. That can be denoted by capital B. B is equal to 0.12340. So we have to compare the exponents of two floating point numbers. Okay. So A value is 3, B value is 1. When we are comparing these two exponents of two floating point numbers, 3 greater than 1, A greater than B, that is nothing but 3 greater than 1. Whenever this condition is true, we have to follow this approach. Suppose this condition is true, A less than B, then we have to follow this approach. Here we have to follow two approaches. The first approach is 10 power minus 1 can be incremented to 10 power 3. Then both exponents are equal. So here the exponent value of first floating point number is 3. Exponent value of second floating point number is minus 1. We have to equal the exponents of two floating point numbers, because whenever these two floating point numbers exponents are equal, then only it is possible to perform the addition or a subtraction of the mantissas. That is nothing but alignment of mantissas. We have to use, among the two approaches, we have to use the first approach. So 10 power minus 1 can be incremented to 10 power 3. At that time, this exponent value and this exponent value both are equal. Then we have to perform the addition operation between the mantissas after aligning the mantissas. Now A value is 3 and B value is minus 1. So A greater than B, that is nothing but 3 greater than minus 1. Condition true. If this condition is true, we have to perform these two steps. Shift right B. That means we have to shift right the content of mantissa of second floating point number by 1 position. And also we are incrementing the exponent of the second floating point number. So these two steps are continuously repeated until both exponents are equal. Okay, how to perform that one? Here first I am comparing the exponents of two floating point numbers, 3 greater than minus 1. So if this condition is true, we have to perform shift right B. So shift right B is nothing but mantissa of second floating point number. We are shifting the content of mantissa of second floating point number by 1 position to the right and incrementing the exponent of the second floating point number. So that is 0.01230 into 10 power 0. Whenever these two steps we have performed, after performing, the mantissa becomes 0.012300 into 10 power 0. Okay. Now, what is the exponent value? Updated exponent value. A value is 3 and B value is 0. Again, we have checked this condition. So, whether A is greater than B or not. So, 3 is greater than 0. 3 is greater than 0. Whenever 3 is greater than 0, we have to perform this step. Shift right on the content of mantissa of second floating point number and incrementing the exponent value. So then we are getting 0.00123 into 10 power 1. After performing these two steps, we are getting the result. Now A value is 3 and b value is 1. Again, we have to check the condition. So 3 greater than 1. Condition is true. Now we have to perform these two steps. Now it becomes 0.0000123 into 10 power 2. After performing these two steps, we are getting this result. Again we are checking the condition. A value is 3 and b value is 2. So 3 greater than 2. Condition is true. Again we are performing these two steps. Then we are getting 0.000012 into 10 power 3. After performing these two steps, we are getting this result. Again, we are checking the exponents of two floating point numbers. So here a value is 3 and b value is 3. So 3 greater than 3. Condition false. Whenever this condition falls, then we have to check either this condition or this condition. So 3 less than 3. This condition is also failed. Next, we have to check this condition 3 equal to 3. Condition true. Okay. So now the both exponents are equal. A value is 3 and b value is 3. At that time, the mantissa of first floating point number is 0.583123 into 10 power 3 and mantissa of second floating point number is 0.000012 and the exponent value is into 10 power 3. Now, so both exponents are equal. Then simply we are performing either addition operation or a subtraction operation. So this is case 1 or approach 1. That means here the exponent value is 3, but here the exponent value is minus 1. Now minus 1 value is incremented to plus 3. Okay, what is the difference between them? 3 and minus 1. So 3 minus of minus 1. So that is 4. So 4 times we are performing the shift right operation on the mantissa of second floating point number. Each time when we are performing the shift right operation, the exponent value can be incremented by 1 of the second floating point number. Finally, we are getting this one. So now the exponent value is 3. Here the exponent value is 3. Both exponents are equal. Now we are performing the addition or a subtraction between the two floating point numbers. Now we can go for this approach or second approach or case. The second approach or case 2 is we are comparing the exponents of two floating point numbers, whether A is less than B. Now we are performing these two steps. Shift left A. That means we are shifting the content of mantissa of first floating point number by 1 position to the left and decrementing the exponent value of the first floating point number. So after performing these two steps, again we have to repeat this step. Again we are checking the exponents of two floating point numbers. If A is less than B, if this condition is true, we are performing these two steps. After performing these two steps, again checking the condition whether both exponents are equal or not. If they are not equal, again we have to check this condition whether A is less than B. If this condition is true, again we are performing these two steps. After performing these two steps, again we are checking the exponents of two floating point numbers. Whenever both exponents are equal, we have to stop the approach to or case 2. Now, whenever both exponents are equal, then we have to perform either addition operation or a subtraction operation between the two floating point numbers. After completing the second step, that is alignment of the mantissas, in that one two approaches we have considered. This is the first one and this is the second one. Okay, these two approaches are used for equal the exponents of two floating point numbers. Whenever both exponents are equal, then only we are perform the operation such as addition or subtraction between the mantissas. Now we can go for third step, addition or subtraction of two mantissas. Suppose we are performing the addition operation. Now we have to check the sign bit of the two floating point numbers. Only we are considering mantissas. Okay, so sign bit of the first floating point number is mantissa is represented by AS. Sign bit of the mantissa of second floating point number is denoted by BS. Okay, here for comparing the sign bits of the mantissa of first floating point number and the second floating point number, here we have to use XOR gate. So what is the speciality of XOR gate? When both signs are same, then it becomes when both signs are same, its value is 0. When both signs are different, its value is 1. Now we have to consider these cases. So in these two cases, mantissa of first floating point number and mantissa of second floating point number signs both are same. Next, here in this case, mantissa of first floating point number and mantissa of second floating point number signs are also same. Plus plus, minus minus. In these two cases, we are performing the addition operation. So that is A plus B. Plus A plus B is nothing but A plus B. Minus A plus minus B is nothing but minus of A plus B. In these two cases, we are performing the addition operation. When both signs of mantissa of two floating point numbers are equal, then its value of the XOR gate is 0. Then only we are performing the addition operation. Whenever we are performing the addition operation between the two mantissas, simply, so this is the mantissa of first floating point number, this is the mantissa of second floating point number. Okay, when both signs are same, then we are performing the addition operation. 2 plus 2, 4, 3 plus 1, 4, 5 plus 7, 2 with carry 1, 0 plus 0 plus 1, 1.244 into 10 power 3. Okay, if any carry is generated after performing the addition operation, any carry is generated, that carry bit can be transferred to extended flip-flop. Okay. Here the sign bit of mantissa of first floating point number, sign bit of the mantissa of second floating point number, both signs are same. At that time, after comparing the mantissas of signs of two floating point numbers, so the output of the exclusive OR gate is 0. Okay, at that time we have to simply perform the addition operation between the mantissas of two floating point numbers. Whatever the result we are getting, that result is transferred to A. If any carry is generated, that carry bit can be transferred to extended flip-flop. Okay, now we have to check the E value. Okay, so this can be done in fourth step, that is nothing but normalizing the result. Now we are already there in the step 3. Okay, next one. Suppose in this case both signs are different. Okay, mantissa of first floating point number is minus, mantissa of second floating point number is plus. Another case, mantissa of first floating point number is A and mantissa of second floating point number sign is minus. Both signs are different. In this case, we have to perform the subtraction operation. Okay. In these two cases, we are performing the addition operation. In these two cases, we are performing the subtraction operation. So both signs of the mantissas of two floating point numbers are different. At that time, the output of the exclusive OR gate is 1. So whenever the output of the exclusive OR gate is 1, then we are performing the subtraction operation. Okay, how to perform the subtraction operation? For performing the subtraction operation, so A minus B, so it can be written as A. Subtraction operation is nothing but addition operation by complementing the subtrahend, that is B bar. After that we are adding 1. So whenever both signs of the two mantissas of two floating point numbers are different, the output of the exclusive OR gate is 1. So in this case, we are performing the subtraction operation. So A plus B bar plus 1. If any carry is generated, that carry bit can be transferred to extended flip-flop. Okay. Suppose we are performing the subtraction operation. For performing the subtraction operation, we have to find out the 1's complement plus 1. After performing that one, simply we are performing the subtraction. 2 minus 2, 0. 3 minus 1, 2. So 1's complement of B is nothing but B bar. After that we are adding 1. 1's complement plus 1 is nothing but 2's complement of B. So then we are adding that complement of B to the A. Then we are getting the A minus B. A minus B is nothing but A plus B bar plus 1. Here minus can be converted into plus by taking the 2's complement of b. A plus b bar plus 1. This can be done when both signs are different. When both the signs of mantissas of two floating point numbers are different, the output of the exclusive OR gate is 1. At that time, we are performing the subtraction operation by taking the 2's complement of b. After performing the 2's complement of b, that can be added with the a. So then whatever the result we are getting, that result can be transferred to a. If any carry bit is generated, that can be transferred to extended flip-flop e. In this way, we have to perform the addition operation. Here in the case of addition operation, we are considered two cases. The first case is by comparing the mantissas of signs of two floating point numbers by using XOR gate. The output of the exclusive OR gate is 0 when both signs of mantissas of two floating point numbers are same. At that time, simply we are performing the addition operation between the two mantissas. That result can be transferred to a. If any carry is generated, that can be transferred to extended flip-flop. When signs of mantissas of both floating point numbers are different, so in this case, so the output of the exclusive OR gate is 1. At that time, we are performing the subtraction operation. Subtraction operation can be done by using 2's complement. So a plus 2's complement of b in this way. So whatever the result we are getting, that result is transferred to a. And any carry is generated, that carry bit can be transferred to extended flip-flop. Now, suppose we are performing the subtraction operation. Suppose we are performing the subtraction operation. Again, we are checking the two conditions. By comparing the sign bit of the two floating point numbers mantissas, the output of the exclusive OR gate is 0. Simply we are performing the subtraction operation. Here when sign bit of mantissas of two floating point numbers are different, at that time the output of the exclusive OR gate is 1. Then simply we are performing the addition operation between the mantissas of two floating point numbers. Whatever the result we are getting, that result can be transferred to a. If any carry is generated, that carry bit can be transferred to extended flip-flop e. Next, when both signs are same, plus a plus b minus a minus b, at that time we are simply performing the subtraction operation. Plus a minus plus b is nothing but a minus b. Minus a minus of minus b is nothing but minus a plus b. That is nothing but b minus a. So whenever the sign bit of mantissas of two floating point numbers are same, we are performing the subtraction operation. At that time, the output of the exclusive OR gate is 0. So how we are performing the subtraction operation? We are taking the complement of second floating point number plus 1. So then we are getting the 2's complement of second floating point number, that can be added with the mantissa of first floating point number. Whatever the result we are getting, that result can be transferred to a. If any carry is generated, that carry bit can be transferred to E. So in this way, we have to perform the either addition operation or a subtraction operation between the two mantissas when both exponents are equal. Okay, so this step can be called as addition or subtraction between the two mantissas. Okay, now we can go for the fourth step. Fourth step is nothing but normalizing the result. Okay, in normalizing the result, after performing the addition operation, we have to performing the addition operation, whatever the result we are getting, that result can be transferred to A. If any carry bit is generated, that carry bit can be transferred to extended flip-flop. So at that time, we have to check E value. Suppose E value is equal to 0, that means no carry is generated. So we have to simply stop the procedure. That means nothing can be happened. We have to end the process. Suppose E value is equal to 1. That means any carry is generated. What steps we have to follow? These 3 steps we have to follow. Okay. First one is shift right A. We are shifting the content of mantissa of first floating point number. Then whatever the E value is there, that E value can be transferred to A1. A1 is the most significant bit of the mantissa of first floating point number. Then we are incrementing the exponent of first floating point number. So after performing the mantissas of two floating point numbers addition, we are getting this result: 2 plus 2, 4, 3 plus 1, 4, 7 plus 5, 2 with carry 1. So here the carry bit is generated. So the carry bit is 1, that can be transferred to E. E is nothing but extended flip-flop. Okay, so whenever the carry is generated, so this condition is called as overflow condition. Okay, when we can say that overflow condition is occurred after performing the addition operation between the mantissas of two floating point numbers. If any carry is generated, that can be transferred to E. Whenever E value is equal to 1, so that means overflow is occurred. Whenever overflow is occurred, we are performing these 3 steps. Shift right operation performed on the mantissa of A. Whenever we are performing the shift right operation on the mantissa of A, then we are getting 0.1244. Okay, whenever we are performing the shift right operation on the mantissa, so then simply we are incrementing the exponent value. So 10 power 3 becomes 10 power 4. Next one, whatever the E value is there, that E value can be transferred to A1. What is E value? E value is 1, so that 1 value can be transferred to A1. Okay, so these 3 steps we have to follow whenever E value is equal to 1. Whenever E value is equal to 1 is nothing but overflow is occurred. Whenever overflow is occurred, first we have to perform the shift right operation on the mantissa of first floating point number, that is by 1 position, that is shift right A. Next, we are incrementing the exponent of the first floating point number, that is a equal to a plus 1. Next one, whatever the e value is there, that can be transferred to a1. After performing these three steps, so what is the result we are getting? So this is the result we are getting. Okay. So after performing these three steps, now we have to check the most significant bit of the mantissa. Most significant bit of the mantissa is 1. 1 is nothing but it is a non-zero value. Whenever the most significant bit of the mantissa is a non-zero value, we can say that so this result is normalized result. This floating point number is normalized floating point number. So that is the fourth step. After performing the addition operation, then whatever the result we are getting, that result is normalized result. Okay. For saying whether the result is normalized result, we have to check the e value. If e value is 1, we can say that carry bit is generated. Whenever carry bit is generated, overflow is occurred. Whenever overflow is occurred, we are performing these three steps. After performing these three steps, whenever we are getting the most significant bit of the mantissa is a non-zero value, then we can say that the result is normalized result. The floating point number is also a normalized floating point number. Then we have to stop the procedure. Whenever e value is equal to 0, so no carry is generated, we have to end the procedure. Whatever the result we are getting, that result is normalized result. Okay, next. Here, after performing the subtraction operation between the mantissas of two floating point numbers, now what is the result we are getting? So 2 minus 1, 1, 3 minus 2, 1, 5 minus 5, 0, 0 minus 0, 0. This is the result we are getting, 0.011 into 10 power 3. Okay, so any carry bit is generated, that carry bit can be transferred to extended flip-flop E. Now we are checking the E value. Okay, suppose E value is equal to 0. So here no carry is generated. E value is equal to 0, no carry is generated. At that time we have to perform these two steps. A equal to a bar plus 1. A equal to a bar plus 1. And next one is complementing the sign bit of the mantissas. Okay. So after performing these two steps, again we are checking the A1 value. A1 is nothing but most significant bit of the mantissa. Okay, so if its value is equal to 0, so now check the most significant bit value is 0. Okay, if it is 0, now we are performing the shift left operation. Okay, whenever we are performing the shift left operation, so what we are getting here, so 0.110 into decrementing the exponent value. So then we are getting this result, 0.110 into 10 power 2. After performing this step, now we are checking the A1 value. Now A1 value becomes the 1. Okay. So whenever A1 is nothing but most significant bit of the mantissa. If its value is 1, simply we have to stop the procedure. That means we are getting the normalized result, because most significant bit of the mantissa is a non-zero value. We can say that the result is normalized result. The floating point number is normalized floating point number. Okay, so we have to check the A1 value. If A1 value is equal to 0, most significant bit of the mantissa value is 0. It is not normalized. Okay, to get the normalized result, we are performing these two steps. Shift left operation performed on the mantissa of first floating point number A. After that, we are decrementing the exponent value. After performing these two steps, again we are checking the A1 value. Okay, if A1 value is 0, repeat this step. If A1 value is 1, then we have to stop the procedure. Now the result is normalized result. Okay, so this case is called as underflow condition. Okay, after performing the subtraction operation, we are checking the most significant bit value. If the most significant bit value of the mantissa is 0, then it is underflow condition. Whenever underflow condition is occurred, that means A1 value is 0. That means most significant bit of the mantissa is 0. Then we are performing this shift left operation performed on the mantissa and decrementing the exponent. Okay, these two steps are performed repeatedly to overcome that underflow condition. So whenever the most significant bit of the mantissa value is 1, then we can say that we are getting the normalized result. Then this normalization step is completed and we have to end the process. Suppose this can be done when E value is 0. Suppose when E value is equal to 1, that means if any carry bit is generated. Okay, so if any carry bit is generated, now we have to check the A value. Okay, so if A value is 0, A is nothing but resultant value. Okay, after performing the subtraction operation, no carry is generated. Any carry is generated, that means that carry bit can be transferred to E. Now E value is equal to 1. At that time, we have to check the result. Suppose if the result value is equal to 0, then 0 can be transferred to accumulator. Okay, suppose A value result is not equal to 0, then we are checking the A1 bit. So if A1 bit value is 1, the result is normalized result, then we have to stop the process. Suppose A1 value is equal to 0, the result is not normalized. We are performing these two steps until the most significant bit value is equal to 1 in the mantissa. When A1 value is equal to 1, we have to stop the end procedure. We have to stop the process. So this step is nothing but normalization of result. Okay, so normalization of result is nothing but after performing the addition or subtraction operation, we have to check E value. Okay, when E value is equal to 0, nothing can be happened. When E value is equal to 1, these three steps we have to follow. This step is nothing but normalizing the result. Okay, whenever we are performing the subtraction operation, any carry is generated, that carry bit can be transferred to E. Now we have to check the E value. E value is 0. These two steps we have to follow. After performing these two steps, check the most significant bit of A1 value. If it is 0, then we are performing these two steps until A1 becomes 1. Okay. Whenever A1 is equal to 1, we have to stop the procedure. When E value is equal to 1, check the result value. So if the result value is equal to 0, then the 0 can be assigned to the accumulator. We have to stop the procedure. Okay. So in the normalization process, okay, in which case overflow is occurred, in which case underflow is occurred. If overflow is occurred, what steps we have to follow? If underflow is occurred, what steps we have to follow? Okay, this can be discussed in this normalization step. Okay, so these are the 4 steps we have to follow for performing the floating point addition and subtraction. First one is a check for zeros. Second one is alignment of mantissas. Third one is addition or subtraction between the mantissas. And fourth one is the normalizing the result. So this is a big question, but if you can understand carefully, it is very easy. For better understanding of this flowchart, so please refer the previous video, floating point addition and subtraction. If you understanding that video, it is really helpful for understanding this flowchart. I hope all of you understanding this video. If you really understanding this video, please share this video to your friends and classmates. If you really understanding this video, please subscribe my YouTube channel, Divvela Srinivasa. After subscribing my YouTube channel, click on the bell icon to get the future updates in my YouTube channel. In the comment box, I am giving the playlist of computer architecture or our computer organization and architecture links. Please go through these links in the comment box for better understanding of this entire subject, and watch these videos and get more marks in the examination. After subscribing this YouTube channel, click on the bell icon to get the future updates in my YouTube channel. If you have any doubts, please put your doubts in the comment section. I will try to clarify your doubts. Thank you one and all for watching this video.